into a function. That means we have to do the same for the mean and the covariance matrix as well. And basically we have to now have a mean function mu of x and the covariance function kappa of x and x prime. And the reason why we need to do this is because that's basically the only way you can kind of fill in all the gaps, right? So you have to remember that now you could add any function evaluations you wanted to this distribution, right? If you want to evaluate it at a new point, we can't just kind of explicitly parameterize the covariance matrix. Now we have to have a function that allows us to, on the fly, compute what's the covariance between points. And I'm going to go over this a couple more times, so hopefully by the end some of it will stick. But this is basically a Gaussian process that's defined by a mean function and a covariance function, so like a univariate mean function and a covariance function that has two arguments. And I'm going to I made some visualizations last night that I hope will kind of explain this connection a bit better. If so, then I'm glad, otherwise I wasted the night. Oh, yes, and also this doesn't work just on a line, like all the examples are on a line, but of course you can define a Gaussian process on some vector inputs as well, because you just define a kind of function from a different space to reals. Okay, so this was the covariance matrix. Just take it as given. One thing I wanted to highlight is the reason that this kind of looks like it has a lot of structure is because I kind of cheated because I know where I want to go with it. I could have just the same showed you this covariance matrix. It describes exactly the same set of random variables, just with some permutation of the indices, right? So I can just permute the order of elements in our vector function values. Maybe someone gave you the training data set sorted, maybe they didn't. So these effectively represent the same distribution. But what we're going to do next is we're going to replace the indices I and j that go from 1 to 6, and we're instead just going to call it x1 to x6. So these are the indices, and what we're modeling is the function values at those indices. Right, so now actually, if we model functions, then we know where did we measure those function values, so we can put those on the axis instead. And now we kind of have to stretch this kind of 5 by 5 covariance matrix and put it kind of embedded in the full space of a covariance matrix where both x1 and x2 kind of go to infinity. So that's what I plotted here. So it's kind of like infinitely dense and infinitely extended. And if I kind of think of how does this covariance matrix fit in here, then I basically just have to take this element, which is at 0.25, 0.25, and then that kind of goes through here, and I can do this for all the elements, and yeah, that's basically how the kind of covariance matrix of 5 functional evaluations fits in with the covariance function that kind of describes the distribution over functions as a whole. And we can kind of go back by just choosing a subset of indices, x1 to x6, and looking at evaluating the covariance function at those points, and then that gives us the finite dimensional covariance matrix back. Okay. Hopefully that was useful. So going back from visualizations to the more formal, sorry, that's the other thing. So the only thing that's changed again is like the permutation and the indices down here. All right. No, I forgot one more thing. I wanted to also talk about how does this relate to draws from the distribution. Yes. So this is the same visualization we had before, just for this covariance matrix. And again, you can kind of do the same thing of embedding these on draws of actual functions. So here is kind of draws from a function. And these are the finite dimensional subsets on which we had evaluated the function before and how they connect with each other. Yes, and so for these visualizations, I basically sorted the indices so that they kind of nicely come one after the other on the real line. That's basically just an artifact of it being something I do in 1D to put on the screen. If I had scrambled the indices, then we'd basically be connecting points that are not next to each other. So, but it doesn't matter for the actual learning of function. All right, so going back to kind of a bit more formal notation, Gaussian process is a distribution over functions from some fairly arbitrary domain x to the real values. So commonly this is some kind of real space of d dimensions, but it does not have to be, so you can build Gaussian processes on strings, kind of on functions that take a string and give you a value back. You can do Gaussian processes over graphs for basically any object for which you can define a mean function mu and the covariance function kappa. You can use that as a Gaussian process model. And those two functions completely characterize the distribution over functions given by the GP. And similar to the finite dimensional case, the mean function basically gives us the mean of the distribution, and the covariance function evaluation gives us the covariance of the function values. So again, this is kind of a point that's a little bit maybe tricky to understand when you first encounter Gaussian processes. But the kind of important thing to understand here is that we have a covariance between function values, f, but we parameterize this covariance based on the inputs x. So basically, the covariance function kind of defines how similar are different points on the space, right? So if the similarity is high, then that corresponds to us kind of saying like, okay, the function value at x and the function value at x prime should be roughly the same because x and x prime are similar. And that could be, for example, because they're close to each other. Or if you have a time series problem because like one is exactly 1 year after and you have some seasonality. All right. Yes. And then this is just basically the maths for kind of going back from the infinite dimensional distribution over functions to the vector of function values at some finite subset. So that's just the multivariate Gaussian where the mean vector is the mean function evaluated at your points, and the covariance matrix is the covariance function evaluated at your points. And yeah, so this is kind of how we get a distribution over infinitely many random variables all at once. But in practice, we only ever deal with a finite subset, right? So like the mathematical object is infinite, but our training data sets are finite, the points on which we can make predictions are finite, and the points I can put on the screen are finite. So like we can actually deal with like just these finite dimensional subsets. Okay, so yes, so I talked about covariance function and how it kind of encodes similarity. And really, the covariance function is at the heart of Gaussian process models. Another word for covariance function is kernel or kernel function. Sometimes you see people use both in a paper or only one, but they're effectively the same thing. It's a function from 2 points in your arbitrary input domain that gives you one real value for each pair, and then that allows us to construct the covariance matrix. And this covariance function, that's what encodes our kind of prior beliefs over functions. Of kind of like, what do we believe the data generating latent functions actually look like? So this is kind of specified by the covariance function, and you'll see some examples in a minute. And so what types of prior knowledge might we be able to encode? Any thoughts? Smoothness, very good. Anything else? So we could encode, for example, whether a function is that the function is continuous. We could encode that it's once differentiable or twice differentiable or infinitely many differentiable. We can encode that we believe our functions should be periodic. So I briefly mentioned seasonality. So we could say like, okay, we want to model functions that have a daily periodicity because we want to model temperature or like biological kind of properties that have a daily rhythm, and any other kinds of invariances that you can think of, symmetries of your problem, and so on. So there's a wide range of prior knowledge that you can encode with the right choice of covariance functions. What unfortunately happens a lot in practice is that people don't really think about this property of GPs, and they're just like, oh, let's take the kernel that I read about in that paper yesterday, which is probably the squared exponential kernel, which also has a whole bunch of other names. So you might see it referred to as Gaussian kernel, exponential quadratic kernel, or even RBF kernel. RBF is, I think, a terrible choice because that just stands for radial basis function. And the squared exponential kernel is a radial basis function kernel, but there's plenty of others as well. So I think that's unfortunate, misleading naming and should be banned, but people still keep doing it. So the squared exponential kernel looks like this. If you plot it as a function of the distance between the two arguments, and it only depends on this distance. It's an isotropic kernel, and that implies that kind of there's no underlying directionality kind of like in your domain a priori, and that's the important point, right? This is a priori before you actually learn from data. So like using this does not mean that your posterior is going to be isotropic. It just means that before you see any data, you have no prior beliefs over which direction should be preferred. Like most covariance functions, this one has two parameters. In this case, this prefactor sigma squared, and this factor in the denominator of the argument L squared. And these are hyperparameters, so they kind of affect the properties of the functions. So for example, in this case, L squared is kind of the squared, or L is the length scale parameter, so that kind of says like over what range do correlations extend in your data, kind of in your domain. So if the length scale L is short, then points, or basically like points that are kind of much further away from each other than this length scale are basically uncorrelated. And hyperparameters is something that you can learn from data. I'll briefly get back to that later. But it's important to know that covariance functions do have hyperparameters, so you have to kind of think about them existing. All right, so as I just said, like it's not the only kernel. You probably should think a little bit harder about what do you actually believe over your function. I'm not going to be able to go into details of what covariance functions there are, so I'm just going to like briefly show you this visual representation of samples from Gaussian processes with different covariance functions. And you'll see that some of them are basically linear, so Bayesian linear regression is basically the special case of Gaussian processes. Some of them are basically non-differentiable. Some of them are stationary. Some of them have a trend. Some of them are periodic. Lots of choices. Like, not the time here to go into details, but basically take away from this, there are many covariance functions, and you probably want to kind of think about like which one's right for your problem if you want to use the Gaussian process. All right, so this is, I think I'm running a bit behind schedule. This was all about Gaussian processes as a distribution over functions. I haven't even talked about learning from data yet, right? So let's do that next. So learning from data in a Bayesian setting, like we generally start with a prior. If you have kind of a parametric model, you start with prior distributions over what do you believe your different parameters to have as values. Now we're talking about learning a function directly from data. So now we have this Gaussian process prior over functions. And you saw kind of some examples of those priors on the previous slides. Now we want to combine them with data so we can actually learn from data. So for that we need an observation model, often just called the likelihood. And the likelihood defines how, how our observations, our observation targets relate to this latent function that we want to learn. So here, the bold Y is kind of like the vector of all the observations in our kind of the training data set outputs, and then the bold F is the vector of kind of function values at the training data set features or inputs. And then often we make this kind of factorizing assumption that given the latent function, all the data points are kind of conditionally independent. So that's the kind of generative model. What do you do in Bayesian models if you want to learn from data? Yeah, so you get the posterior, the one theorem this, which is Bayes' theorem, and that's basically just saying like, okay, like the probability distribution over kind of what's the function given the data that we've seen. That's given by the likelihood term, P of Y given F, times the prior P of F, and then because it's a probability distribution, we have to make sure it's normalized to 1. Here, I've kind of explicitly conditioned on where did we actually make our observations. That's kind of the input matrix big X. Often people also just ignore that, but it does depend on actually where did you observe your training data, not just what you observed. And then the second thing that I still omitted here again is the hyperparameters, for example, of the covariance function. And those go basically in every little bit here. All right, so that's the model. And then this is kind of the example we had at the start. If we actually kind of crank the algorithm, and I'll go into how to crank the handle of the algorithm in a second, then this gives us the posterior distribution over functions given the set of training data. So I wanted to kind of highlight how important encoding your prior beliefs is. So this is the fit that you get. We can kind of do it in closed form, showing like the mean and the spread of the uncertainty of our posterior. This is what you get if you use, for example, a squared exponential kernel. You model kind of smooth functions, and then away from the training data, it just goes back to the mean. But that's not the only choice. So you could, for example, use a covariance function that encodes non-stationarity, and then draws from that posterior would look like this, and the mean keeps going up outside of the training data as the variance is also increasing. Or you could say like, okay, I believe there should be periodicity in this data set, and if you use a periodic kernel, your prior beliefs are just periodic functions. So the posterior is going to be those periodic functions that are compatible with our observations, and then that looks like this. So these are 3 different fits, look completely different, all for the same training data. What changed? Just the covariance function. So that's why I was kind of hammering down on like, think about what the covariance function is. How do we actually do inference in this model? We start with some training data, input-output training pairs X and Y, and then often we kind of combine them in this matrix big X and the vector Y. Now, we usually assume that there's some observation noise in the data. So in the simplest case, in Gaussian process regression, we just assume that this is additive noise. So that the kind of latent function values are corrupted by this additive noise with zero mean, and some noise variance, sigma epsilon squared. So what do we care about? We want to know what's the posterior mean and variance at an unseen test point X star. So now I'm going to just do it for one test point, but in principle you could do it for all the test points you wanted to do in one go. And I'm briefly going to go through the 3 steps it takes to get the posterior. It's not actually that hard, it's just the 2 operations that we talked about at the start, marginalizing and conditioning. So we want to basically get the posterior mean and variance of f star, which is the function evaluated at the test point, given the training data. So step 1, we write the joint model. So the joint model is just the kind of joint probability distribution of all the things that there are. So there's the kind of observations y, vector of observations y. Then there's the vector of latent function values f at where we measured the y. And then the third one is f star, that's f at where we want to predict. Now, actually writing this down, we can split this into the likelihood of p of vector y given vector f at the training data, then times the kind of joint prior over p of vector f at all the training points, and as well adding kind of the extra random variable for f star at x star. So that's the joint model. For the additive Gaussian noise, this is a normal distribution for the GP. This is kind of like the finite, the marginalization of the function everywhere at to only those points that are the training points and the test point. So both of those are Gaussians, and then the product of 2 Gaussians is also multivariate Gaussian distribution. So that's step 1, the joint model. Now here we've assumed 0 mean. I'll skip over that for now. And the important part is this kind of block covariance matrix. So there's one block for kind of the covariance across training points, then the off-diagonal block for the kind of cross covariance between training points and test point, and then there's the block down here for the kind of self-covariance of the function value at the test point. So they're just different sets of evaluations of the covariance function. So that was step 1. Step 2, now we have to marginalize out f at the training points, because we don't actually care about that right now. I mean, you can also look at the posterior at the training data, but usually that's not the most interesting part. So marginalizing out just means we integrate over it. And in this case, if you do kind of the linear algebra, it basically just means we add this kind of diagonal matrix of the noise covariance to the KFF matrix, that's the covariance of the training points. So that's step 2. And then step 3, so now we end up with a distribution over just y and f star. The vector f disappeared. And then step 3 is to go from the joint distribution to the conditional distribution of p of f star given our observations y. This is, again, a Gaussian distribution with some mean and some variance. And the equations are down here. They are pretty much the same as you had in the multivariate Gaussian slides half an hour ago. Again, like, don't feel like you have to memorize them right now, right? Like, the main reason I show them here is because you also see them in basically every single Gaussian process paper, or whether it's a methods paper or an application paper, somewhere people put something vaguely looking like this in. So if you don't memorize it right now, don't worry, you'll see it over and over if you actually end up doing anything with GPs. Yeah. So that's it. That's 3 steps that allow us to kind of do posterior inference in a Gaussian process model. And that brings me to GPs as an algorithm. So basically just that, right? Plus some kind of practical bits. But yeah, one important point is that the posterior in the Gaussian process model with the Gaussian likelihood is also a Gaussian process. So you could kind of just, you end up with the same type of optic as you had before. So that generally makes for nice maths. Right. Yes. And so next I wanted to show this online demo. So here, here is an interactive visualization. You'll see the link at the end of the slides. This here is visualizing the prior distribution of a Gaussian process with kind of 3 continuously varying random draws from the GP. So we talked about different covariance functions, so you could choose a different covariance function. Now all the draws are parallel functions. Or now all the draws are kind of non-differentiable functions that are still continuous. So let's go back to something a bit smoother. So this is the prior, and now the 2 lines of linear algebra I showed on the previous slide, that's what allows us to condition on observation. So if we add 1 observation here, now all that's left is functions that are compatible with this observation. So I could add multiple observations, and then that kind of restricts like what functions from the prior are still compatible with the data, and then that gives us the posterior distribution. So here you'll see that all the functions actually go exactly through the data. That's because we had 0 observation noise. If we add a bit of observation noise, you can see that the variance kind of increases a bit, and they don't go through all the data points anymore. What happens if you have noise in the training data, but you don't actually account for it? Well, then your model might go a bit haywire. So this is where, okay, and I think I crashed. And it crashed the browser window. So that's what happens if you assume that there's 0 observation noise, but actually there's, because then you're basically forcing your model to interpolate through every point, and the numerics of the linear algebra become unstable. That's why it crashed. Yes. So that's why it's important kind of like make the right modeling assumption. All right. So the other thing I can show here is kind of like the effect of the kernel hyperparameters. So here we have the length scale. If we make the length scale long, then the functions have like longer range correlations. If the length scale is short, then there's no long range correlations. And again, if we have some data points, then which length scale you choose significantly affects your posterior. All right, so you can play around with that afterwards later. So that was that. So what about the hyperparameters? How do we actually select them? One option is to just use expert judgment. That's kind of what I did. I was just like playing with the settings until it looked right. That may be a valid choice. Like if you have a domain expert who can tell you like, oh, I expect kind of correlations in my data to disappear after when points are more than some units away, then you can just use that. Alternatively, you can just be Bayesian about the hyperparameters themselves. If you can't get a point estimate from the expert, maybe they can help you figure out what's a reasonable range of values for the length scale hyperparameter or the noise that we expect to have in the data, and then you could do inference over the hyperparameters as well. You can also do something more kind of classical machine learning, use cross-validation to figure out which values of the hyperparameters best explain the validation sets. But actually, what people usually do in Gaussian process models is to use the marginal likelihood. So we learn hyperparameters by maximizing the log marginal likelihood with respect to the hyperparameter values. The marginal likelihood is kind of the probability of the data by itself, kind of integrating over the latent function values. So that's why it's called the marginal likelihood. We marginalize over the latent function values, and now we are left with the kind of probability of our observations given some choice of hyperparameters. And because we had the Gaussian process model that if we marginalize over everything is still Gaussian, we can write this down in closed form and just use, for example, a gradient ascent with autodiff on this equation and use that to find the point estimate of the hyperparameters. So just wanted to point out, like just for the prediction equations, we have this inverse of an n by n matrix and the log determinant of an n by n matrix. That will become challenging if you have larger data, and I'll talk a bit more about that in a second. But kind of just to summarize, what do we need for Gaussian process regression? We need a kernel and a mean function that define our prior and some hyperparameters for those kernels and mean functions. And what I want you to remember is that the kernel does not have to be a Gaussian kernel. The mean function, often people just say like, oh, we assume a zero mean prior. That's a reasonable assumption if you've normalized your data so that your training observations have zero mean. But if you didn't normalize your data or you don't want to normalize your data, then a zero mean prior assumption is a bad prior assumption and you'll get a bad fit. So the mean function does not have to be zero. It can be constant, it can be linear, it can be a neural network even. But either way, you need the mean function and you will make some assumptions by what you pick. And then lastly, you need hyperparameters and they need to have some values. If you use a Gaussian process package, often the default values are just 1. That's probably a terrible assumption for your concrete data set, so you should not just leave it at the default values. You should either ask a domain expert or use some way of kind of finding the optimal values of them, or be Bayesian about it and do MCMC. And I mentioned data pre-processing on the slides because often, like, it's just easier if you kind of normalize your data for all the input features to be zero mean unit standard deviation, for the training outputs to be zero mean and unit standard deviation. It just kind of tends to make the numerics easier. All right, so that was a lot about what's the Gaussian process. Before I move on to the sharp bits, any questions at this point? Yeah? Yeah, that'll be 3 slides from now also. Other questions on what is the Gaussian process? How do I do inference in GP? All right. So sharp bits that might be a bit annoying with Gaussian processes. First one is practical issues. For example, initialization of your hyperparameters before you optimize them. I'll talk about that very briefly. Then what you just asked about, how do we scale this to large data? If we have an n by n matrix and we need to invert it and n is large, what do we do? So that's generally cubic in the number of training data for the computation and squared in the number of data for memory requirements. And in my PhD, I worked on Gaussian process models for molecular modeling, and for us it was actually not the cubic compute cost, it was the squared memory cost that was the bottleneck. So this was almost 10 years ago. We got a machine with 2 terabytes of RAM, which was very, very much at the time, and I think even now you'll only have like a few nodes in a high-performance computing cluster that have that much RAM. And we needed 2 terabytes of RAM just to be able to basically do the matrix inverse. So that was kind of like at the edge of what you can do with Gaussian processes. Right, so this is infeasible kind of if you do it naively for more than a few thousand data points. There's lots of ways around it. So I'll briefly cover that. Then the third point is so far I just assumed, oh, like our observation model is the latent function got corrupted by additive Gaussian noise. And in practice, that again might not be a good assumption for your use case. Maybe your observations are positive, you know they have to be positive, maybe they're even discrete, maybe you're modeling like counts of gene expression and you know it's an integer number larger than 0, like what do you do? So first part is like you can build better observation models, but then the second kind of part is that then if you have a non-Gaussian observation model, then the posterior is not as nicely available in closed form, so you have to kind of do approximate inference. That's number 3, and then the fourth part, I think I'll have to be quite quick, as kind of like when is a Gaussian process a good model for representing the functions. And a GP is generally good if you can specify a meaningful prior. So if you can kind of think about your problem and you know like, okay, there's like some periodicity or stationarity or smoothness or something, then a Gaussian process is useful. If your input domain is images, then it's probably hard to kind of say like, okay, what's my prior belief over functions from images to our function output. And then Gaussian processes might not be like as easy to apply. All right, so for the first issue about initialization, I just wanted to point out that we briefly saw that you can use the marginal likelihood to optimize hyperparameters. Now, the marginal likelihood is generally a multimodal function. So this is an example I took from the Gaussian process book that I'll also put on the slides later. But basically, they plotted the marginal likelihood as a function of the length scale of the kernel and the noise standard deviation of the observation model. And you can see that there's 2 local maxima here. Now, the first maximum is the one that has a large length scale and the highest standard deviation. That's this one. So here, like all the functions are kind of long-range correlations, but there's quite a lot of kind of observation noise in the specific model. So that's kind of saying like, oh, we have high aleatoric uncertainty. There's lots of variation in the data that we cannot explain with our model. The other maximum of the marginal likelihood is this one. And that one is saying like, oh, the length scale is short, but also the noise standard deviation is short. So now we're saying like, oh, there's like low aleatoric uncertainty. We can actually explain like all the training observations very well, but there's high epistemic uncertainty away from the training data because we haven't seen anything around here, and we believe that our correlations tail off very quickly, so knowing about the functions here or here does not tell us much. Sorry, I was pointing from. So the function values here and here don't tell us much about what's going on in the middle. Right, so marginal likelihood is multimodal. If you use this to optimize your hyperparameters, then it matters where you start. If you start somewhere over here, you'll probably end up here. If you start here, you'll end up here. Right? So this is just something to keep in mind. Lots of things you can do about it. You could add kind of priors or constraints to guide the optimization. You could use multiple restarts to basically try out different points of the hyperparameter space or starting points and figure out where do they end up. Yeah, and I have another demo here. So this is different data sets, so the function looks a bit different. But again, you have like several nodes here. There's actually 3. And you can see like typically you have kind of like one node that's small length scale, small noise, one node that's kind of longer length scale, higher kind of noise assumption in the observation model. And I've got the link for that in the slides as well that you can play with later if you're interested. Okay, right. So that was the first caveat. The second one is scaling GPs to large data. I'm going to skip over the details. There's lots of things you can do. I'm not even going to read them out. Don't look at them now because it's distracting. But the important point of that was you can deal with large-scale data and Gaussian processes. It just depends a lot on the specifics of your problem, and without actually discussing with someone who knows about GPs about your problem, it's kind of hard to say. So if you think a Gaussian process is in principle the right tool for the job, then probably you can make it work for large-scale data, but you might have to talk to a GP expert, so don't worry about the details. Same for non-conjugate likelihood models. You can still do inference in these models. The classic one is Markov chain Monte Carlo for sampling. That usually works, but kind of goes in the opposite direction of computation scalability, so that tends to be quite expensive. There's a Laplace approximation that in neural networks recently has become quite popular, and you can also use that in GPs. And then there's other variants such as expectation propagation or variational methods. And again, no details here, it's just kind of keywords for if you think, okay, I want an observation model for kind of preference data, like all I know is someone liked this better than that, or all I know is counts. There are ways you can deal with it, and you'll probably just have to talk to someone or read more about it then. Yes. So I'm going to skip over that. Basically, just if you can't specify a meaningful prior directly, then GP might not be a good tool for the job, but you can also use them as building blocks. So a colleague of mine, for example, worked on computer vision, where they used the Gaussian process for the part where you're kind of modeling the angle of a camera observing a scene. So there we have a lot of physics knowledge about how should things change under rotations and translations of the camera, and then they combine that with the neural network for doing the actual kind of computer image modeling. Right. So that was some caveats. Now, I'm sorry I'm running late as well, but now I want to just briefly recap kind of why would you want to use Gaussian processes. So firstly, because they are a flexible, nonlinear way of learning functions from data. Secondly, because they allow you to be Bayesian about the function learning, and that means we can handle small data sets very well. So especially on small data sets, GPs are actually really nice to fit, and in that case, they're also actually very fast compared to figuring out how to fit a neural network to not overfit to your data. So GPs tend to be reasonably robust to overfitting. They also have this kind of connection that I briefly mentioned to linear regression. So they're kind of a generalization of linear regression and spline-based models, and you can kind of think about GPs as infinitely wide neural networks. So there's kind of a bunch of theoretical reasons for wanting to use GPs as a kind of Bayesian building block for learning functions. Then they allow us to capture the uncertainty that we still have about this function. So one sharp bit I should have maybe mentioned before. So standard Gaussian process regression assumes that the noise variance is the same everywhere in your domain. And when that's not the case, so when your variance of the noise kind of changes depending on where you observe, this is called heteroscedasticity, then again, it's just a thing that you can handle with GPs, but if you kind of use the vanilla, the noise variance is the same everywhere, then it's not going to handle that so well out of the box. The next reason to like GPs is because if you have prior knowledge, then they allow you to kind of encode that in the model. Like I briefly mentioned, this is not just if your input domain is d-dimensional real space, but it's also the case if your input domain is, for example, strings, whether that's gene sequences or protein sequences. You can use it for graphs, learning from graphs, and anything else for which you can kind of define what's the similarity between two objects. Gaussian processes are mathematically tractable, so you can actually do things with it rather than like even more complex models where then we can't do anything. So we get closed form inference, and the posterior is also GP, and they have nice properties. I probably put too many things on this slide. Yes, the last one I wanted to highlight. Let's do it this way. So Gaussian processes are closed under linear operations, like addition or taking the gradient of the function that you're trying to model, or integrating the function you're trying to model, or projecting it onto some other space. And that means we can both learn from like gradient observations and integral observations, but we can also predict them. So there's plenty of use cases where like you want to predict the gradient, but you can't actually measure the gradient. So with the GP, you can kind of like learn from the function values and predict the gradient, or learn from the gradient and predict the function values. Lots of flexibility. I already put too much into the slides, but there's so much more that we didn't even have a chance to get into. So one is, how do we construct these covariance functions that allow us to encode our prior beliefs? Second one is kind of like, we talked a lot about the function values, not so much about what are the covariates, like the kind of inputs to the function. So with Gaussian processes, you can kind of determine like how relevant is which input feature to the predictions. So there's things called like ARD, automatic relevance determination kernels. There's other approaches as well. I didn't really manage to talk about like how do you use GPs as part of a more complex model. So I'm going to skip over that. And like kind of various connections that you have from a more theoretical point of view to other models, such as state space models that Mihaela briefly mentioned. So you can kind of, there's a connection between Gaussian processes and state space models as well. Yes. All right. So by time I should stop now. Are you willing to stick around for a little bit longer for some examples? Yeah? Good. Okay. All right. So the first one is protein expression across different conditions. What we have observed here is kind of like the relative expression of some protein as a function of time. And then, because messy biology, they repeated it 3 times. It's also hard to do an experiment, so they didn't want to do it more than 3 times, so 3 is all we got. And you'll see that for one protein in one condition, this is a grand total of about 30 data points. So that's not a lot. Something that you'd probably struggle, like finding a good neural network for. But that's something that's like a good use case for Gaussian processes. So what's the task here? So the experimentalists, the biologists want to find out, is this protein differentially expressed under 2 different conditions? So we put the protein in solution A, we put it in solution B, and we want to figure out this, or we put the cell into solution A, put the cell into solution B, and we want to see does the amount of protein A kind of change over time in a different way depending on which condition the cell is in. So in this case, you can see like, okay, yep, the blue condition looks like this, the red condition looks like that, so that's clearly different. The challenging bit is that sometimes they got data like this, right? So there's like one experiment that looks quite different, and then it's a bit less conclusive whether they're really different or not. If you ask an expert, they look at this, they're like, oh yeah, probably something went wrong in this one experiment replicate, so we should throw this one away, and then we see that all the others match up, and this one is not differentially expressed. So that's fine. The problem is that they have lots and lots and lots of proteins, that they all want to analyze in one big go because they have these big, I forgot what they called, microarrays or something. So they wanted something where they can automate it and let the computer figure it out. Now, if we just fit a Gaussian process to all of those, sorry, oops. If we fit the Gaussian process to all of those, then it's kind of going to do something in the middle. Oh, I really should have changed the order of slides. All right, so the point being that if you're just kind of naive about it, you're just throwing all the replicates in one bag and you fit the Gaussian process to that, well, it's kind of going to somewhat average it out, and then your model is going to tell you like, oh, they kind of look a bit different, when they're actually not, because it's just one outlier in the set of replicates. So one thing you can do here is kind of make your model a bit more complex. So here we've just got a kind of one-dimensional GP like you've seen plenty of times in the previous slides, where now the x-axis is time, and the function value is kind of relative expression. And we can kind of artificially extend the space. So we can kind of say like, let's have an extra dimension for how much of an outlier is this specific replicate. Now we have a bivariate function of time and outlierness, and we can build a kernel for that. And that basically now describes a whole kind of set of functions, one for each potential value of outlierness. And if we now fit this to our data with an outlier, then it actually allows the model to kind of learn, okay, this one's very different from the others, I should kind of push it further away in outlierness dimension, and then kind of like the best fit model ends up matching the kind of like what the expert would say as well. So the model can then kind of automatically say, oh, this one we should probably discard. So I'm just going to kind of show this is what happens if you have the kind of basic GP. So we fit one GP to the condition A in blue and one GP to the condition B in red. And then depending on your threshold, your model might say like, okay, they're clearly different here, so it's differentially expressed. If you use the kind of more bespoke model that accounts for a replicate might be an outlier, then the two GP fits actually agree very well, and the model could confidently say like, yep, they're probably just the same regardless of condition. So that was kind of one small little example that I put together at the GP Summer School last year in an evening. So like building GP models doesn't have to be hard. Yeah, that was like a small side thing. The other example that I wanted to show, just to kind of show what is the extent of things you can do with GPs, is a much bigger project. So this is about the causal modeling of treatment outcome sequences. So follows on quite nicely from some of the things that Mihaela mentioned. So here we're looking at things as a function of continuous time. We have treatments that could be like you take a medicine at some dose. In our example, the treatment was actually meals and how much you eat. And then the outcome is kind of like maybe like a biomarker that changes both kind of by itself, but also in response to the treatment. And in our example, that was blood glucose. So blood glucose, there's kind of like some background behavior, and then when you eat a meal, your blood glucose a little bit after that starts going up, and then eventually it decreases again. But then also, the outcomes might affect future treatments, right? Like when your blood glucose goes down too much, you start getting hungry, you have another meal. Or if you take a medicine, if you have another lab visit and the doctor says like, oh, maybe you have to like take another course of medicine or something. So what we wanted to do here is basically model all these different interactions, both how does treatment affect the outcome, how does an outcome affect future treatments, and also how does an outcome affect kind of like when a treatment might next happen. And for the details, I'm going to refer you to our paper, which just got accepted at ICML. I've got the link there. But yeah, so the point of like building this complex model with different parts is that it allows us to actually do, like kind of look at the details of what's going on. So now you could kind of say like, okay, like how your blood glucose affects your meals, and vice versa, kind of depends on like a policy, such as kind of like what's your diet, for example, or in the other setting, kind of like what does a specific doctor tell you to do. And now we can kind of look at the separate parts of all these interactions, and then, for example, predict like, okay, how would your blood glucose change over time if you were on a different diet, for example. And by kind of not just having a big black box model that tries to do everything at once, and instead kind of constructing a model with kind of smaller Gaussian process building blocks for different functions, we can separately model what's the kind of blood glucose background levels, what's the response of blood glucose to a single meal, and kind of like how do they add up together. And yes, this kind of gives us a much more interpretable model that still fits the data very well. And that was just coming out at SML in Hawaii this year. Right. So at the very last, if you think this is something that might actually be useful in a problem you've got, where to go next? First, there's at this point quite old book, but still has basically all the basics that you need by Carl Rasmussen and Christopher Williams, and it's also freely available online. Then there's two kind of distilled.pub style articles. The first one is kind of more like what I talked about today, kind of intro to Gaussian processes. The second one, a practical guide to Gaussian processes, is a bit more about kind of application-specific things like, okay, how do you set the hyperparameters? And then the last one is the interactive demo I showed. So I'm hoping we can put the slides on later. And there's lots of software packages depending on what framework you like. And in about 2 months, there is the Gaussian Process Summer School just over east of here. So if you're interested, I would highly recommend signing up to that. And that's it.
So we've eaten into our lunch a little bit, but maybe let's just have one question, and then other questions can be over lunch.
I'm still here till Thursday.
So if anyone has a burning one, or if people... And T's here for the whole thing, so just grab T and ask about everything GPs while you're here also.
Hi, thank you for this. It was really interesting. Maybe I may have missed it. You drew a lot of comparison at the start to Bayesian linear regression. I was wondering, would this allow for adjustment for other covariates in the model, so for example sex, or do we just build different GP for each sex? Is that how it works for this?
Yeah, so it kind of depends what you want. So you can build, like the simplest case is probably building kind of separate individual models, but you can also build joint models and kind of build more complex kernels, more complex covariate functions that kind of model how you believe the different covariates should interact with each other. Yeah.
Would that be similar to what you were talking about earlier about, sorry, in the example about latent modeling, where they would then draw out that how the different...
That's one way, yeah. So basically it kind of comes down to how do you build the model. Like it's kind of hard to say in the generic case, if you have something concrete you think about, you can discuss in the break.
That's right. Thank you very much.
Okay, I think we'd better have some lunch, so let's thank T once more.